2.2, and we're going to look at a couple limits to start with. So this is example 1. The function f of x is going to be 2x plus 3 over x minus 1. And the question is, find the horizontal asymptote. F of x is 2x plus 3 over x minus 1. And the question is, find the horizontal asymptote. Okay, so you've done this problem before in pre-calc. But the method they taught you only works with certain types of functions. So I'm going to teach you the method that works with any type of function. The problem is you remember the other method, well, some of you remember it pretty well. So I don't want to talk about it too much, but does anybody remember how to find the horizontal asymptote? This is the old method that I want you to forget. That's kind of a loaded question now. Okay, Stephen, I want you to forget it, but yeah, what is it?
Is it where you set the bottom equal to 0 to find out what x, so x is equal?
That's the old way to find vertical asymptotes. But good. A horizontal, so he's remembering vertical asymptotes. So does anybody remember the old way to find horizontal asymptote? Yes? Yeah, so you look at the leading coefficients, and since the top and the bottom have the same power, x to the first and x to the first, then 2 divided by 1 is 2. So it turns out the horizontal asymptote is 2, y equals 2. That method only works on some functions, and it's the old way, and I want you to forget how to do that. Okay? So if I ask a question, find the horizontal asymptote, it's not enough just to do it that way, because you got to do it the calculus way. Okay, so the calculus way is to take a limit. So what you do is you take the limit as x goes to infinity of the function. And you also take the limit as x goes to negative infinity of the function. So obviously they couldn't teach you this method in pre-calculus because you didn't know what a limit was. So that's why they taught you this other method. But from here on out, these two processes are how you find horizontal asymptotes. Okay, so taking a limit as x goes to infinity is something that we haven't done yet. But we have done where the limit came out to infinity. So remember last week where we did one limit, I think it was even on day 1, so the Friday a week ago. So we plugged some numbers in over here, and then this went 6 and 66 and 666. So it kept getting really, really big over here in the y column. And that meant that the limit was infinity. So we've had a limit come out to infinity, but we haven't had x go to infinity. But it's pretty simple. To make x go to infinity, all you do is you pick numbers that get bigger and bigger progressively towards infinity. So you could pick 6 and 66 and 666 if you wanted to. I usually go with 10, 100, 1,000. So x going to infinity just means pick some x's that get progressively larger and really, really big. So now we're going to take those and plug them into f of x. So as normal, in the first period, we got like f of x in the back here. So don't forget parentheses. We're just taking 2 times 10 plus 3 divided by 10 minus 1. So I got 2.556. good with the 2.556? You sure? Remember, it takes guts to admit that you don't know what's going on. I'm always impressed, especially on Monday morning. So I'm trying 100 and I got 2.051. And then I'm going to try 1,000. And I got 2.005. So these are getting closer and closer to 2, right? All right, so now I'm going to plot these points. Kind of strange to plot those points, but I've got my function f of x here. And I'm going to plot 10, 2.5. And then I'm going to come way out here, and I'm going to have to exaggerate because I can't go out to 100, so I'm going to put 100 here, just kind of out there farther. 100, 2.05. And then I'm going to plot 1,000, 2.005. So I got 3 dots, and what's happening to those dots? Yeah. Yeah, they're coming down this way, and the graph is getting closer and closer to 2. That's what an asymptote is, right? And so I sometimes draw in this dotted line here to show that this line is coming down and getting closer and closer to the line y equals 2. So that dotted line y equals 2 is called a horizontal asymptote. So the official way you know that is, since you took the limit and it came out to 2, that means, so this limit is 2. The technical calculus way of knowing that there's a horizontal asymptote as 2, at 2, is because this limit came out to 2. So there is a horizontal asymptote at y equals 2. So the reason I know this is from this table here, not from the coefficients. It's okay to check with the coefficients, but again, that is a specialized method that just works on some functions, and also it's the old way to do it, and we need to learn the new way to do it. So here's your work for that. Okay, now it's possible that down here to the left, there's a different horizontal asymptote. So that's why it's necessary to calculate this limit as well. Some functions will have a different horizontal asymptote on the right as opposed to on the left. So this is needed as well to check to see if there's a second one. So raise your hand if you can tell me what numbers I should put in the x column here. Yeah, Connor? Yeah, negative numbers that do what? Exactly, they get bigger towards negative infinity. So if you want to be unoriginal like me, you could do negative 10 and negative 100 and negative 1,000. So now I'm just going to go back and plug those 3 things in and see what I get for those. So for negative 10, I got 1.545. For negative 100, I got 1.950. And for negative 1,000, I got 1.995. So what are those getting close to? 2 as well. So that means there's not a different horizontal asymptote. But it is possible that these would have been getting close to something different. That's why I had to do this work as well. So it further confirms that there's a horizontal asymptote at y equals 2. And it also tells us that back here, the points are coming up towards 2 like that in the graph. How did I know it was coming up from the bottom instead of coming down from the top? Because these numbers are less than 2, right? 1.95 is below 2, and 1.5 is below 2. Okay? So again, I can't emphasize enough that you might remember the old way to do this problem, but you need to know the new way, because the old way doesn't work on every function. AP can cook up some functions that this method of deleting coefficients doesn't work. But it's good to know if you remember it, because then you can always check. Okay? Okay, so let's summarize that. This is now a fact that we're going to write down that could go on something you needed to memorize. So the function f of x has a horizontal asymptote at y equals b when the limit as x goes to infinity of f of x is b, or the limit as x goes to negative infinity of f of x equals b. The function f of x has a horizontal asymptote at, not sure why I wrote as there, at y equals b, when the limit as x goes to infinity of f of x is b, or the limit as x goes to negative infinity of f of x is b. So yeah, maybe put a star by that or something. Whatever you do to study for tests, you make note cards. I like note cards because then if I just have a sheet that I'm looking at, and the answer is there, my brain says, oh, the answer is there, I don't need to memorize that. But if I have a question on a note card and the answer is on the other side, then my brain is, this is the way my brain works, I don't know about yours, then my brain has to think about what the answer is before I turn the card over. So just staring at this doesn't help me. But anyway, whatever works for you. So this is something you need to know. Okay, so Stephen, when I asked about horizontal asymptotes, brought up something about vertical asymptotes. So we're also going to talk about vertical asymptotes today. So that's horizontal asymptotes. So let's see. We're going to have f of x. So this is example 2. So this time f of x is x squared plus 2x minus 1 all over x minus 3. And the question is, find the vertical asymptotes. Okay, so the old way, the pre-calculus way to find a vertical asymptote was to look at the denominator and to figure out when it comes out to 0. So we're still going to do that, but it's not just that. Okay, so anyway, let's set the denominator equal to 0. So you're going to remember this because this is the old way of finding vertical asymptotes. And then obviously the denominator comes out to 0 when x equals 3. However, in the past, you just stopped here and you said, that makes it a vertical asymptote for sure. And that's not completely true. It was true for the functions you were looking at, so it was okay that they told you that. But now we need to know the complete picture because we're more sophisticated. Okay, so this means that there might be a vertical asymptote at x equals 3. So this is tricky for people because in the past you were able to stop here and say, since the denominator comes out to 0, that means there's a vertical asymptote there. But that's not okay to stop there this year. Okay, so what you have to do after that to confirm whether it is a vertical asymptote or not is you have to take a limit. So we're going to calculate the limit as x goes to 3 of f of x. So 3 is a good candidate for a vertical asymptote, but we don't know for sure yet whether it is, and that's why we're calculating this limit. Okay, so in order to calculate that limit, you need to pick some numbers that are close to 3. So like 2.9, 2.99, and 3.1, and 3.01. Okay, so I need a volunteer for 2.9 for a couple reasons. I want to learn some names. And first of all, it gets boring if I'm just talking. So. Okay, you are Kylie, you said? Okay, Kylie Steinberger? Okay. Sometimes if I put the last name with it, I'm more likely to remember. Okay, so Kylie, you've got 2.9. Okay, I need a volunteer for 2.99. You're Jack? Okay, you got 2.99. How about 3.1? You're Colin? Okay, you got 3.1. And then you're Annie? Okay, you got 3.01. All right, everybody else type in one of them. Don't just sit there, because you might fall asleep because it's Monday morning. I mean, I don't know how you could fall asleep in this class. It's such a riveting. I mean, I'm such a engaging person that everybody would just stop by to say see you and say hello to. So I can't believe anybody would fall asleep. But in case you're falling asleep, maybe it's a little early to share this with you, but my dream as a teacher is for the lectures to be just so enthralling that people want to stop by to see them. And you guys would be the privileged ones because you already have a seat, but then people who just stop by would have standing room only, right? But they'd be fine. They'd be like, oh my goodness, I got into Early's lecture first period. It was amazing. I'm not quite there yet, as you can tell, but I'm getting there, right? Pretty close. Yeah. Okay, so anyway, 2.99 is negative 132.1. Oh, now I was asking for volunteers and that stuff. Is that what you got?
Yeah.
Sure, she's going to say that no matter what. Okay, 2.99. Jack, what do you got? Negative 1,392. Good. All right. And 3.1 was Colin, right?
Yeah,
148.1. And Annie, what'd you get for 3.01? 1,481? Cool. Thank you. Oh, sorry. Thank you. Okay. So what's going on here? For 2.9 and 2.99, what's happening? 132, then 1,392. What do you think, Stephen? Going towards negative infinity, that's right. If you weren't sure, you could plug in 2.999 And I think that would give us like 13,920 or something like that. It would just keep getting progressively larger and negative. Okay, so the limit as x goes to 3 for picking numbers that are smaller than 3. So the way to write that is that, right? Of f of x is negative infinity. And then for the bottom half of the table, the limit as x goes to 3, picking numbers bigger than 3, of f of x is positive infinity. Because these are getting progressively larger and larger. Everybody doing okay? Okay, so what that means is, if you try this limit and it comes out to negative infinity or infinity, that confirms that there's a vertical asymptote there. So it's possible that these would have been getting close to 2, and then it wouldn't have been a vertical asymptote. But since these are getting close to infinity or negative infinity, then it confirms this as a vertical asymptote. Okay? So now, based on this information and based on this table, we know there is a vertical asymptote at x equals 3. So let me say again, in the past you might have stopped here and said, okay, the bottom comes out to 0, so I know there's a vertical asymptote. But that's not enough to prove that it's true for sure. You only know that it's a vertical asymptote for sure when these limits come out to either infinity or negative infinity. Okay? And again, those methods were okay for the past because they picked problems that the methods worked on. So that it's not a problem that that's the way you did it in the past, but now we're getting more sophisticated, and so we can do vertical asymptotes and horizontal asymptotes on more types of problems. Yeah?
Why is it not horizontal asymptote? It has to come out to a number, but a vertical asymptote.
Because for a horizontal asymptote, the points need to be getting closer and closer to a flat number. Because that's what the graph is doing if it's hitting a horizontal asymptote. Whereas for a vertical asymptote, when you're close to the number, you want it to be going like crazy up or going like crazy down. So that's just because of what it looks like on the graph, that's why this is happening. Actually, I think I got this backwards from the left on this one. It's going to negative infinity, right? And from the right, from the 3.1 and the 3.01, it's going to positive infinity. And so it has to do with what the graph looks like. Good question. Yeah?
Since the limit of x would be smaller and bigger, does that mean that does not exist?
That's true. It is true that this limit here does not exist. That is correct. So if I just ask you for what that limit was, your final answer would be does not exist. But since one side came out to infinity and the other side came out to negative infinity, or if they'd both come out to infinity, or if they'd both come out to negative infinity, it confirms the vertical asymptote. Right. What matters is the fact that it was going to negative infinity and or positive infinity. Good. So it would be possible to have a does not exist limit where one side was going to 3 and the other side was going to 7, and then that wouldn't be a vertical asymptote. But if you have a does not exist limit where it's going to negative infinity and positive infinity, then it is a vertical asymptote. Good. So what Ashley's getting at is, what's this fact that I need to write down for vertical asymptotes? So that's what we're going to write down next. Okay, so f of x has a vertical asymptote at x equals a when the limit as x goes to a is either infinity or negative infinity. F of x has a vertical asymptote at x equals a when the limit as x goes to a of f of x is either positive infinity, bless you, or negative infinity. Now technically this wasn't happening on that problem, right? Because it wasn't infinity from both sides, and it also wasn't negative infinity from both sides. So if I want to be complete, I also have to say that it's possible that the limit just from the left is either infinity or negative infinity. Or the limit from the right is either infinity or negative infinity. Yes.
Would it be like if you're coming from the left, it would be from the right, it would have to be negative infinity?
Not necessarily. It's possible to be going to infinity from both sides. So there are some graphs that look like that. So yes, that's why I included this, because it's possible. Good question, though. So all I'm saying down here is maybe just from one side it goes to infinity. And then it's still a vertical asymptote. Or maybe just from the other side it goes to infinity. And then it's still a vertical asymptote. Everybody doing okay? Okay. All right, so one of the two new things today were vertical and horizontal asymptotes, but also I kind of slipped in there limits going to infinity. So that was new. We hadn't taken a limit as x went to infinity. So I just need to make a couple comments about limits towards infinity. So all the limit laws still work if x is going to infinity. So what I mean by that is, the other day we wrote down that the limit of f plus g was the limit of f plus the limit of g. So we said you can distribute limit past plus. So that was one of the limit laws that we had. So now today what I'm saying is that still works if there's an infinity sign there. So you can still distribute limit past plus even if the limit's going to infinity. And I say that for a couple reasons. Number one, we hadn't seen this before, where x was going to infinity. And number two, it just kind of reminds you, oh yeah, we did limit laws. I don't want to forget about those, etc. Yeah?
Will we ever have the instances where the limit is as x goes to infinity of x?
Sure, yeah. And since it's the table y equals x. then 10 is 10, and 100 is 100, and 1,000 is 1,000. So it's going to infinity, yeah.
So one of those limit as x approaches infinity of x plus limit as x approaches infinity of like 3. We just write down infinity plus 3.
No, that's infinity.
Okay, so you just,
Because if you plug 10 into that, you get 13. And if you plug 100 in that, you get 103. And then 1,003. And those are just going to infinity. So infinity is a concept. So you can't really add a number to it. But I guess if we wanted to get into it, which we don't really want to because it's beyond the scope of this class, I guess infinity plus 3 is still infinity. Because of what I said, 13, 103, 1,003. So infinity isn't a number. It doesn't work like other things because you can add something to it and still get infinity. Okay, last problem we're going to do is example 3. And we're going to calculate the limit as x goes to infinity of sine of x over x using the sandwich theorem. Okay, so I think it's been a while since we talked about the sandwich theorem, so let's remind ourselves what that says before we try to do this problem with the sandwich theorem. Okay, so sandwich theorem is an if-then, because it's a theorem. So you already have this in your notes. You don't necessarily have to write it down again. You can flip back and look, or you can write it down again, whatever you want. So there are two requirements for the sandwich theorem. Does anybody remember what one of them was? Kristen, looks like you got it there. Do you know what one of them is, or? Okay, good. So the way I said it in English was trap the function you care about in between two other functions. So in this problem, the function we care about is this, sine of x over x. Okay, and the fancy way to say, the mathematical way to say trap your function in between two other functions is to say your function is f of x, and it's less than another function, and it's bigger than a third function. So the mathematical way to say it is g of x is less than or equal to f of x is less than or equal to h of x. But Kristen's exactly right. The English way to say it is, here's my function that I care about trapped between two other functions. Okay, so that was the first requirement. All right, so then what was the other requirement? Yes, Kyle? So the second step, good, is to take the limit of this and also the limit of this. And if the sandwich theorem is going to work, those two limits have to be equal. So the second requirement is that the limit of g of x has to equal the limit of h of x. So the sandwich theorem kind of skirts the issue. You never actually calculate the limit of the function you care about. you only calculate the limit of these two other functions. And then what you get for free is, if these are equal to each other, you get that this limit is the same thing as those limits. Okay, so let's try this over here. So first job is to get this function that we care about trapped between two other functions. Okay, and I'm going to start out using this fact. Now it seems like I'm just pulling this out of thin air, which in some ways I am, because it's just something that I know. So how do I know that this is true? Okay, let me ask a different question. What does the graph of sine of x look like? Looks like a wave, right? And how far up does the wave go? To 1. And how far down does the wave go? To -1. So if you picture the graph of sine of x over x, it always waves in between 1 and -1. So that's why I know this is true. It never goes above 1, so it's always less than 1. And it never gets below -1. So -1 is always less than it. Okay, so this is just a fact that I know that I'm writing down. Okay, now if you have an algebraic expression that's true, you can manipulate it in an algebra way and get new true statements, right? So for example, since I know this is true, I wouldn't want to do this, but I could divide by 3 everywhere. Because if I have a bunch of things in line and I divide them all by 3, they're still going to be in line, right? So if I start with the true statement, I can manipulate it and get new true statements. Okay, but 3 is not what I want to divide by. What I want to divide by instead is x. The reason I'm dividing by x is because then in the middle, I get sine of x over x. Why did I want to get sine of x over x in the middle? Yes, you. Because that's the function I care about, right? That's the one I'm trying to trap in the middle. So I'm there, and then here I just have 1 divided by x, and here I just have -1 divided by x. Okay, so now the first step of the sandwich theorem has happened. I've got my function that I care about trapped in between two other functions. Okay, then the next step is to take this limit and that limit, right? So I'm going to calculate the limit as x goes to infinity of -1 over x, and I'm also going to calculate the limit as x goes to -infinity of, no, I'm not, still infinity of +1 over x. So I'm just calculating this limit and that limit. Oh, I forgot to mention something at the beginning. Isn't this limit just 1? I thought we had that one memorized. Why not, Elijah?
It's for as x approaches.
That's only for when x is going to 0. Good? So way back when we had this limit as x goes to 0 of sine of x over x, and that limit is 1. We have that memorized. But if the limit's going to infinity, then it might be a different answer. Okay? If you got that extra little circle on the end, it changes everything. Okay, so now we're calculating these limits. Okay, these limits are easy. X going to infinity means I just got to pick bigger and bigger numbers, right? -1 divided by 10. It's going to be -0.1, right? -1 divided by 100. -0.01. -1 divided by 1,000. -0.001. What are those getting close to? Getting close to 0. Good. So that answer is 0. Then 1 divided by 10, 0.1. 1 divided by 100, 0.01. 1 divided by 1,000, 0.001. So that's getting close to 0 as well. Why am I glad that these are the same number? Yes, Michael? Because that's what the sandwich theorem says has to happen. If that didn't happen, then I'd be in trouble because my requirement 2 wouldn't be working out. So now I've got both of these requirements, which means that automatically now I know that the limit I care about is also 0. Really what's going on here is if you take a number divided by a huge number, it's going to be close to 0, right? That's all this says right here. If you take a number divided by a huge number, like a billion, it's going to be pretty darn close to 0. Same thing if you take a negative number divided by a billion. It's going to be negative, but it's going to be pretty darn close to 0. That's all that's going on there. Is everybody doing okay? Are you sure? Yes. Sorry, Colin.
I just don't understand the purpose of doing all that work for the sandwich theorem when you can just find it.
Well, the problem here is technically you can't do, I mean, sine of x oscillates between -1 and 1. And so that limit doesn't exist. And if you take does not exist divided by a really big number, I'm not sure what that is. But I do know that a solid number divided by a really big number goes to 0. So the short answer to your question is, well, first of all, the sandwich theorem is important. And so I need to have us practice that. So that's one of the purposes of this example. But the second thing is, we're trying to become really mathematically technical. So yes, a lot of times we have a gut feeling about what an answer is, but what we're trying to develop is a way of showing without any doubt that the answer we think it is true. And that's what's going on. So you're right, you had a gut feeling maybe that the answer was 0, but the answer isn't the important thing here. What's important is the process behind it and being able to prove to the entire mathematical community that something is true no matter what. And that's why calculus is different, because the answer is not necessarily the important thing. It's the process to get there, which is a pain. So, thanks for asking.